I'm Samira and I'm happy to welcome you all to this talk by Prashant Kumar on the histories of mathematics and the archival record. To briefly introduce Prashant, he's a historian of histories, science. Prior to joining the archives at NCBS, he was a postdoctoral fellow in global intellectual history at Humboldt University in Berlin. He received his PhD in the history of science in 2021 from the University of Pennsylvania, during which he was also a visiting scholar at the University of Cambridge and a pre-doctoral fellow at the American Philosophical Society. He studies the relationship between power, politics, and the creation and use of new knowledge in the mathematical sciences. His previous work has examined the role of caste in structuring hiring and work patterns at Madras Observatory during the colonial era. Over to you, Prashant. Thank you so much.
Thanks, Samira, for that introduction. Thank you all for coming. This is, I think, as close as it gets to a sold-out crowd for a talk on the history of mathematics. So thank you for coming. And thanks to Madan and everyone at the Simon Center for letting us use this space. I should also say I owe a special debt of gratitude to Anjali over there, who is our archivist, who's helped me navigate this massive 100-year-long collection. So, as Samira said, the title of this talk is Histories of Mathematics and the Archival Record, and it came about because the archives at NCBS, just downstairs over there, has recently acquired the papers of B.S. Madhava Rao, who was a mathematician based at Central College in Bangalore. So he began as a mathematical physicist and then transitioned into pure mathematics per se. I'll be talking about the early period of his work in the 1930s and 40s, where he worked on what are called relativistic wave equations. In particular, his collaboration with Homi Bhabha and an episode of controversy which arose much later. So just to explain this little cartoon, his notebooks are full of these little undated cartoons here. So you can see he said, physicists solving unsolved problems. How many? 80. No, 10 to the 6. No, 10 to the 7. Why? What? How? Where? Nonsense. I don't really get it. I think the implication is that no matter how many unsolved problems you solve, more still arise. And then down here we have a boulder chasing what I assume is George Sudarshan up a hill. So he was a good friend of Sudarshan, and Sudarshan obviously worked on problems in thermodynamics having to do with entropy. So, I wanted to start by just giving a general introduction to the history of science as a field per se. So the question is, what is the history of science the history of? Is it a history of facts? Is it a history of people? Is it a history of discoveries? So I want to illustrate this with an example. So let's say we're walking along, and there's a plot of grass over to the right. And let's say I ask you, is the number of blades of grass in that plot, does it exist? Does that number exist in some sense? Show of hands. Who thinks the number exists? Like in some platonic sense. Show of hands? Show of hands? Okay. Some people. What if I told you that in order to verify that number, you'd have to get down on your hands and knees, and you need to count every single blade of grass. But when you do that, there will be problems, right? I mean, maybe there'll be some blades of grass that are much, much shorter than others, so you'll define a cutoff. Let's say there's a strange blade of grass that forks into two. Is that one blade of grass, or is it two, right? The point is that prior to your counting the blades of grass, that number doesn't exist. That number is the result of choices, particular decisions, right? And in the history of science, we call this the social construction of knowledge. We don't mean that gravity doesn't exist. We don't mean that, social forces, people, categories totally determine knowledge, but choices and conventions do, and they shape the size of that number. Point one. The second point is that history, at least the way I think of it, is not about explaining how we got to now. It's about recovering some sense of possibility from the past, thinking about how things could have happened differently. And in order to do that, what you have to do is forget. You have to remember that you already know how things worked out, but the people that you're talking about didn't, right? And so if you take what you know now, and you subject people in 1930, 1970 to it, in a sense you're cheating. You already know the answer. They didn't. So if what you want to understand is how people come up with new things, you have to forget it. And so this is the ideas from Walter Benjamin. So our story concerns two characters, one not very well known, generally. Who had heard of B.S. Madhava Rao prior to this? Again, show hands. One person. Right. So he's a local boy, as you can see from his first name is very literally Bangalore. He was born in 1900. He did his undergraduate education in Bangalore, did his master's at Mysore University in the 1930s. And so he applied for Mysore State scholarship to go abroad in the 30s to study in Germany or France. It's not clear from the documents, but it appears he never got it, right? So his early work was on what's called field theories, in particular the work of a physicist known as Max Born, who considered the problem of the electron interacting with itself. When you consider, the way that the electron, which is a negatively charged particle, is influenced by its own charge, certain infinities, divergences occur. So a lot of Born's early work was concerned with this, and Madhava Rao's 1938 thesis, which we actually have a copy of in the archive, tries to formalize some of Born's early work. I'll say more about him as we go. The other character, I'm sure, is well known to all of you. He's much more well known. Homi J. Bhabha. So Bhabha is about a decade senior to Madhava Rao, but couldn't come from a different background. He came from a very, very wealthy Parsi family in Bombay, and by the 20s he had, studied at Cambridge. He initially began in the mechanical engineering tripos because his father wanted him to come back to India and work as a mechanical engineer. He writes a letter to his father saying, "I hate this. I want to do physics. This is what I'm meant to do. Please let me do physics." So then he does the mathematical tripos. And he goes on to do a PhD at Gonville and Keyes in Cambridge. In 1939, he comes back to India just on the eve of the Second World War. And as soon as the war begins, he can't return, even though he's got a postdoctoral fellowship at Cambridge. And so he secures an affiliation at IISc, working under C.V. Raman. So that's the stage set for our two characters. The other thing that's important to know is I'm going to break physics down into just 4 simple categories that we're going to be working with. So to some vague approximation, you can think of physics as divided into these 4 regimes. We have large things moving slowly, right? Large relative to the size of an atom, and slow relative to the speed of light. And so this description was formalized by Newton, his Mechanics in the Principia Mathematica in 1687. For things moving close to the speed of light, we had to wait until 1905 with Einstein's special relativity. So what Einstein points out in 1905 is that there's an inconsistency in Maxwell's theories. If you consider the expressions for within Maxwell's equations for a stationary magnet that has a coil moving past it versus the expression for a stationary coil with a magnet moving through it, they don't agree. And what Einstein points out is that the reason that they don't agree is because within Maxwell's original description, there is a privileged reference frame. Once you do away with that, a whole heap of consequences follow. Key to which is that there is an upper speed limit, and that space and time appear in the same expressions. So by the 1920s, or about a decade or two earlier, what people had noticed was that there were further inconsistencies in Maxwell's theory of electromagnetism. There was what's called the ultraviolet catastrophe, whereby certain expressions that govern the heat radiated by a black body seem to diverge, seeing a pattern here. Physics always throws up these infinities and people need to solve them because we haven't observed anything infinite yet. And so one solution to this, suggested by Planck in the first decade of the 20th century, was to quantize radiation. That is to say, radiation wasn't a continuous quantity, but it appeared in chunks. So instead now, one of the consequences of this was that instead of objects in reality having a defined position in space and time, at the very, very small atomic scale, all you had was a probability distribution over space and time. This, we'll meet later, is known as the wave function. So Schrodinger's famous equation describes how that probability function evolves over time. Now, this was all well and good, but we're still only here. As late as 1930, about 1928, it wasn't known how to reconcile this theory with this theory. When you did so, again, certain divergences, certain infinities began to appear. So people started trying to insert relativity into Schrodinger's equation. Now the history of that is quite complicated and beyond the scope of this talk, but if you read general histories, this process of thinking about how to reconcile special relativity with quantum mechanics for all known particles wasn't completed until the relativistic wave equations for general spin, arbitrary spin, in a paper published in the Reviews of Modern Physics by Homi Bhabha in 1945. My purpose in this talk is to problematize this history and break it down and think about who owns what inside of collaboration? Who does mathematics? Yeah?
Where does Dirac come in?
Dirac is 1928. I've kind of skipped over some of those details. So the Dirac equation describes the motion of relativistic particles of spin half. So those are like electrons and whatnot. What Bhabha does is, and what other people are trying to do through the 30s, is describe the relativistic motion of particles with arbitrary spin. That turns out to be much harder. So we'll get to Dirac in just the next slide, actually. So the 1930s. Here we have the Schrödinger equation. For those of you allergic to mathematics, which actually looks like not very many of you, thankfully. I won't go into too much detail about this, but basically what Schrödinger's equation is an expression of the conservation of energy in some general sense. So here we have the wave function, this probability density function of the space and time that I was talking about earlier. Here we have the reduced Planck's constant, which tells us we're in a quantum regime. Here we have what is known as the momentum operator, which is the generalization of momentum to quantized states. We have potential. And so what this is telling us is that, in some general sense, total energy is the sum of kinetic energy, momentum, and potential energy, right? Now, Dirac in 1928 starts to think about how to reconcile this equation with special relativity, where instead of these independent, so you notice that space and time appear as two coordinates here. That's what relativity changes. Instead of having two separate sort of dimensional coordinates for space and time, you have what's called a four vector, in which space and time transform together. So yeah, you have these partial derivatives. So this is the covariant derivative, the du. M is the particle mass, and what is strange about the Dirac equation and what it introduces that's new are these matrices gamma. So what these matrices do is they introduce a whole, well, two major counterintuitive implications into physics. So these matrices look like this. They're 4x4 matrices, and basically one of the implications is that fundamental particles, despite being point-like, appear to be spinning. They appear to have an intrinsic angular momentum. Moreover, that intrinsic angular momentum is quantized. It appears either as integer values or half integer values. And whether the former or the latter depends, it determines how the large-scale statistics of those particles work. These half-integer spin particles later become known as fermions. They're what makes up matter, things like electrons. And the integral spin particles are what are known as bosons. So we can talk about that stuff later, but the key thing I want to point out about these gamma matrices is that they also imply, so if you solve Dirac's equation initially, you get a whole bunch of what are called negative energy solutions. So there appears to be in Dirac's equation an entire sea of negative energy states. Initially, Dirac thinks that this sea must be completely full because obviously we don't observe these negative energy states. And it's later pointed out that that interpretation is also consistent with an electron of negative charge, that is the positron, right? And this turns out to be an experimentally verifiable implication. So these two things that emerge from Dirac's equation will become key aspects of theoretical physics over the next couple of decades. So the reason it's 4x4 is because you can have spin up, spin down, and you have particles and antiparticles. And all of these quantities transform together within Dirac's equation. So, to switch back to history, one of the key contributors to this early theory of quantum mechanics was, as you see on the left, Max Born. He came up with the Born rules, which describe how quantum mechanics blurs into the classical world. It describes how when you measure a wave function, this probability distribution, you get the classical world. So Born was chair of physics at the University of Göttingen in Germany until in 1933 the Nazis came to power. Born, who was Jewish, lost his position and he was effectively thrown out. His doctorate was rescinded. By the end of the decade, he fled to Cambridge, and he had a short-term fellowship at Cambridge for a couple of years. But at the end of 1935, he found himself without a job. He was a close associate of C.V. Raman, who invited him to come to the Indian Institute of Science, which he did at the end of 1935. And you can see this photo here of him with his wife, Hedy. And they are, I think this was actually taken in Madhava Rao's yard. So he was also a close collaborator because, of course, Madhava Rao had worked on Born's field theories. So back to Madhava Rao, what he was particularly interested in is this issue of nonlinearity in quantum mechanics. So briefly, a solution is linear if A and B are a solution, their composition is a solution. If that's true, you have a linear system. But if I can't compose two solutions and also get a solution, what I have is a nonlinear system. Schrodinger's equation is linear, but it appears that some of the most interesting aspects of physics, for example, as you see here, the scattering of light by light, are nonlinear and can only be explained with reference to these counterintuitive implications of Dirac's equation. So the explanation is basically that when light moves through space, there is the creation of a particle and antiparticle pair, and when another incident light ray meets that there is an interaction between the particle and antiparticle pair. So what Madhava Rao points out in, I think this is 1940, is that one may have to admit the possibility of a future nonlinear character of quantum mechanics. This is not great because nonlinear systems are way harder to work with than linear systems. The first indications of nonlinearity came from the positron theory, and later the avowedly nonlinear theory of Born was devised to meet the difficulties of infinite self-energy. Remember, this is the problem of the electron interacting with itself as it travels through space. So, one of the approaches to this new era of physics was pure mathematics, group theory, and the theory of representations. Many physicists were not happy about this, and in German-speaking circles it became known as the Gruppenpest, or group plague. So this is from John Slater's reflections at the end of the 70s. He says, the mathematicians have made a great study of what is known, called the symmetric group or the permutation group. The authors of the Gruppenpest wrote papers which are incomprehensible to those like me who had not studied group theory. Yet there were no good texts for which one could learn group theory. It was a frustrating experience, worthy of the name of a pest. It's actually a mistranslation. Pest is plague, which is like maybe a little worse. I had what I can only describe as the feeling of outrage at the turn at which the subject had taken. So part of the reason group theory enters, so briefly speaking, a group is a set of n elements where we have a composition operation, we have an identity, and we have closure, which means that if I combine two elements, A and B, and I get a third element, C, C is also in the same set. So, I mean, you can think of a subset of the integers with addition as a simple kind of a group. It turns out that these matrices, these gamma matrices I had put up earlier, form a group, and more generally an algebra over a field. So one approach to studying the solutions of these equations, including the equations for arbitrary spin, was via group theory, via the relations between these matrices. So what starts to happen in the 1930s is that physicists who really, I mean, by that point in the 1930s, their education would only involve partial differential equations, maybe the basics of linear algebra, certainly not abstract algebra and representation theory, which are fairly new subjects, start having to collaborate with mathematicians, for whom, as you saw earlier, they have some scorn. And every physicist acquires a mathematician as a kind of technician. So Bhabha, the eminent physicist, despite being a decade younger than Madhava Rao, begins, while he's at IISc, to collaborate with Madhava Rao. And so in 1940, they write a paper on the scattering of charged mesons. So a meson, we now know, is a particle composed of two quarks, and in terms of mass, it's intermediate between nuclear particles like the neutron and the proton, and the electron. And so what Bhabha was following up on was this idea that it's possible to use a classical analogy. Think about the particles as being scattered by radiation, like in what's called the Compton effect. So Madhava Rao supplied the mathematical machinery that made it possible to calculate the scattering amplitudes in this paper. And thus began their correspondence. It wasn't a totally equal correspondence. So most of the, you might think of it as like mathematical hard lifting was done by Madhava Rao, most of the calculations, whereas Bhabha, because of his connection with elite circles, such as like Robert Oppenheimer in the States and others at Cambridge and Princeton, followed up on certain ideas. He often wrote to Madhava Rao and said, you know, Oppenheimer's group has tried this and they can't solve it, but I heard from somebody else that we should try this. Why don't you do the calculations and send it to me? So this was sort of the nature of their correspondence. And when they wrote this paper, Madhava Rao assumed something of a subordinate role. So Bhabha writes, I should be very grateful if you would kindly do me the favor of correcting this paper for me. I'm anxious that no misprint should occur. So Bhabha was, in a sense, too important to do his own editing, right? But they developed some kind of a closeness. I mean, Bhabha was constantly plagued by health problems when he was in Bombay. So he wrote to Madhava Rao, "The hot and damp climate of Bombay has got me down, and I'm broken out with a number of boils, which have troubled me for the last few days. However, they are now subsiding." These letters are just studded with these constant little updates about Bhabha's boils. So, as you can see here, Bhabha would send Madhava Rao corrections. I think that paper I just showed you went through 4 or 5 proofs, which, I mean, as those of you who've published papers know, this is not a normal state of affairs. I mean, 5 proofs is quite a bit. So Madhava Rao would send the corrected proofs back, and then Bhabha would send further corrections, which Madhava Rao would make and then send to the editor. This was understood as a test. This paper was a kind of test of their collaboration, but also Bhabha's theorizing surrounding the motion and scattering of the mesons. So he writes, "I think the figures should be drawn beautifully by the Institute artist. I'm writing to C.V. Raman to this effect. It will look much nicer." So the figure in question is the one on the poster, which is actually kind of simple. I mean, it's just a theorem in spherical trigonometry. It's actually not totally necessary to include this figure. It has very little to do with the mathematics involved. But this paper was understood by both of them as a kind of debut in the world of meson physics. So after the initial collaboration in 1940, Madhava Rao and Bhabha started to draw apart. Madhava Rao continued publishing on the mathematics involved in generalizing the Dirac equation to particles of arbitrary spin. So he published what are known as commutation rules for these gamma matrices. And in particular, he considered the case of spins 3½ and 2. So recall that the Dirac equation only describes particles of spin ½ such as the electron. There are as yet, and there were then, no known particles of spin 3½ and spin 2. But physicists were interested in the generality of this theory. So this was considered a priority, that the theory should be general in spin. So he says that, you know, I've worked out this method of the derivation of the commutation rules for spins 3½ and the method sketched above is obviously applicable to the case of general spin, although the labor of writing all of this down is going to take too long. So just look at what I've done, and, you know, the rest should be obvious to the reader. You probably recognize the phrase from mathematics textbooks. This turns out to be a strategic mistake. Later that year, Bhabha publishes a paper in which he uses Madhava Rao's method and declares the problem of generalizing these commutation rules to arbitrary spin as completely solved. And at the bottom here, he says that in a more restricted case, as has been done by Madhava Rao, you can work out the commutation rules, but if you follow my method, which he lays out in a short communication in current science, you derive them much more easily. If you read Madhava Rao's paper, it's really, I mean, kind of a laborious process. Now, this all becomes important because many years later, in about the 70s, these particles of spin 3½ and spin 2 start to become important in a nascent branch of physics known as string theory, which predicts that these higher order spins might occur in certain variants of the theory. So in 1974, these two physicists write about this controversy. What they point out is that the first general equations for general spin, were written by Bhabha in 1945 in the Reviews of Modern Physics, which is this flagship journal. And Bhabha goes on to say the alpha, what he calls the alpha matrices, which are the same as the gamma matrices, satisfy these characteristic equations, and they were deduced after relatively lengthy calculations by my technician Madhava Rao in the specific cases of spin 3/2 and spin 2. My argument shows, without any calculation, just kind of show off move, that it is generally true for all spins. And he gives Madhava Rao's paper a little citation at the bottom. So, Madhava Rao, writing now at the end of the 70s, is not very happy about this. So he says, thus the Rev Modern Physics paper of 1945 by Bhabha should, under normal conditions, have been a joint paper by us, since the results obtained therein, and here he says, can't really read it, but he's written, obtained by both of us, were the result of discussions between us. But Bhabha thought it fit to have the paper in his own name, justifying his action, on the ground that he had given complete references to me in the bibliography. What was particularly objectionable was his reference to an important result re alternative masses for the particle. So one of the problems with Bhabha's theory is that it doesn't predict unique solutions for the masses of these particles. It predicts multiple different solutions, and this is something that Madhava Rao couldn't accept because he rightly pointed out that we only observe singular masses for particles, and so he set about on a wild goose chase for these singular solutions. Was his reference to an important result re alternative masses for the particle, originally due to me in a footnote saying, also noticed by Madhava Rao. He goes on to say, and this is a document that he's prepared for his biographer, P. Gupta, who actually also died, strangely. I have ignored for over 30 years all this kind of undervaluing of my work in the interests of scientific propriety and in order to avoid any other rupture, especially with Bhabha. But what this review in the 1970s, which actually stretches to 7 papers, points out, by Krajcik and Nieto here, whom Madhava Rao had been writing to, is that if you look at the mathematical structure, that is the irreducible representations of the group structure that Bhabha's general spin equation follows, SO5, and you break it down into the irreps of lower order groups, you get 2 copies of, for the case of spin 3/2, of Madhava Rao's theory, which you can see here. So within SO5, you can break down the irreps into the irreps of, I'm talking to the mathematicians here, I'm sorry. You can break them down into SO4, and you can break them down even more into SO3, and those were the particular cases that Madhava Rao had worked out. So in the belly of Bhabha's theory, we see here these 2 copies of Madhava Rao's. And so Nieto goes on to say the basic idea for finding the mass states was given by Bhabha. The key realization is that if one puts these gamma matrices into this block diagonal form here, then each eigenvalue block, so these are the eigenvalues in some vague sense, you can think of them as solutions to these, then each eigenvalue block contains a distinct number of composite SO3 spin representations. That was what Madhava Rao had described, these SO3 spin representations. So, as I mentioned, Madhava Rao, seeing this series, writes to Nieto, and he says, the real purpose of this letter to you is, however, to point out that the essentials of what you have called Bhabha's first-order wave equation are all contained in my 1942 paper, the one on commutation rules earlier, published before Bhabha's paper in the Reviews of Modern Physics in 1945. I don't know if you can read that at all, but You have no doubt given a reference to my paper, but this reference implies that I deduced in 1942 commutation relations for spin 3 halves and spin 2 using the Bhabha equations of 1945. Of course, there's a causality error, according to Madhava Rao. Goes on to say, I hope these specific points I have made above will convince you that what you have called the Bhabha first-order wave equation should really be called the Madhava Rao Bhabha first-order wave equation, or the MB equation for short. Just because Bhabha's paper of 1945 appeared in the Reviews of Modern Physics, an internationally well-known journal, my earlier work in 1942, published in the Proceedings of the Indian Academy of Sciences, has been ignored by many people abroad. And he says to Nieto, I request that you kindly set the matter right in case you are convinced with the arguments I have put forward above. Nieto doesn't. He continues to call them the Bhabha first-order wave equations. And in fact, if you read the footnotes in this series of 7 papers by Krajcik and Nieto, he makes no reference to this letter that Madhava Rao sent him. He makes a few minor corrections about the dates, but he doesn't acknowledge the communication, and he doesn't acknowledge the demand that the equations be rechristened. So, what does Madhava Rao do? He's being ignored, he's been marginalized, he's been sidelined. Lucky for him, Bhabha dies young, and he outlives him. And so, in every lecture Madhava Rao gives on this period in the 70s, he massages the history slightly. So, in these preliminary notes from the archives on a lecture he's preparing about Bhabha's life, he praises Bhabha's willingness to learn and his keenness and appreciation of fundamental mathematical ideas. It was a bit of a, low-key burn. He points out that Bhabha was not generous in giving credit to co-workers. My own example. And here in crossed out text, which I don't think you can make out, so I'm just going to read it to you, he says, due to frequent meetings either at Bhabha's hotel, or at the college, or at my residence, this is when they're at IISc, a sort of intimacy grew up between us. Remember the Boyles? And we used to address him as Bhabha, and he used to call me Madhava Rao, without any prefixes like doctor or professor. Sarabhai, Vikram Sarabhai, who had also joined the Cosmic Ray unit and worked under Sir C.V. Raman at the time, was of course more familiar with him, and they used to address each other as Homi and Vikram. You can speculate as to why that was. They did work together a little bit more closely, but they came from very different social positions, and some of this has a role. How much? I won't say. So, in this history that's written by Madhava Rao, as I said, he massages the facts, and he's careful to protect Bhabha's reputation. I mean, Bhabha is being deified at this point, right? The guy dies young, he's involved with the nuclear program. You can't mount a frontal attack on Homi Bhabha even after his death, right? So, what does he do? He says, due to the intervention of World War II, Bhabha could not go abroad back to Cambridge and, perforce, to choose a place for work in India. Perhaps the obvious choice was the Department of Physics at the IISc at Bangalore, where Sir C.V. Raman was the professor, and also at that time there were no squabbles between him and the director of the institute. Another slight burn. Further, there was a strong working group in the Department of Mathematics at the Central College, where Madhava Rao himself was, then affiliated to the Mysore University. In fact, the association with this group and the later association with Harishchandra were in no small measure responsible for Bhabha's later work being more mathematical in nature than his early work in Europe. So I mean, subtly saying that this guy wouldn't have learned the mathematics he needs to make his discovery if it weren't for us, right? And unlike other physicists, Bhabha was not really prejudiced against emphasis on mathematics. It's a reference to the Gruppenpest and the derision some physicists have towards mathematics and mathematicians. And he goes on to say that the turning point for Bhabha towards a mathematical orientation came up as a result of a paper published by B.S. Madhava Rao in 1942 on particles of higher spin. Two of the best known and typical papers are those published in the Reviews of Modern Physics in 1945 and 1949. The basic postulates of Madhava Rao were retained in some modified form or another. Now, unfortunately for Madhava Rao, none of this narrative became general. If you look them up today, they are still known as the Bhabha first-order wave equations. Madhava Rao, in some sense, has remained a footnote, and this controversy is not known to very many people. It doesn't even appear in the 1974 papers. And in fact, as I mentioned, the only reason that this is resuscitated in the 1970s is because some of these equations of arbitrary spin become important in what's known as the adiabatic limit in string theory, where you do get objects with these higher order spins. So people start returning to the early literature. So, what do we make of this? This is the end of the story for now. It's a preliminary one, it's still under construction. But as I see it, there are two takeaways. That the first and maybe easiest is that there is an uneasy relationship between collaboration and credit. Most papers nowadays, even in mathematized parts of physics, biology, what have you, are the result of many people working on a black or whiteboard like that. It's impossible to say who does what. Some person might notice something, some person might work on a little bit of a proof, but when you write the paper, or when awards are given for the work, decisions have to be made about contribution. What this suggests is that the work of doing science and the work of assigning property to what's discovered and what's done may move in different directions. The way that Bhabha treated Madhava Rao as a certain kind of a technician to be used and discarded meant that they couldn't collaborate anymore. Now, things might have been exactly the same, they might have been different, had the issue of property, intellectual property, not come to bear on the question of mathematical structure. So what this episode really suggests to me is that there is a very strange and totally understudied relationship between the mathematics of abstract algebra, group representations, the way that you can find within the belly of other people's theories the remains of other people's theories, and within those theories there are other theories. And this, medieval notion of intellectual property, where everybody builds a fence around what they own and says, this is mine. Those two things seem to be moving in different directions. So, questions. And at this point I might open it to the floor. I'll give you the questions and you can tell me what you think. What is a discovery? How do we bound it? If you discover an equation, how important does it have to be a discovery and not just a contribution? Relatedly, how do you bound that? Is an equation a single equation? Is it a system of equations? Is it the equation and the solutions to the equations? There are some people that have been credited with equations, for example, the Navier-Stokes equations, which we don't have theorems on, the set of all possible solutions yet. They're still getting credit. Who owns it? Who gets given prizes? Who gets invited to talks? Who gets money, prestige, publicity, power in the larger political sphere of science? And how and when, within physics or the sciences generally, do mathematics and mathematicians become tools? When do they supply machinery And when do their contributions become part of the science? What is the relationship between, if you want to divide them in this way, mathematics and science, mathematics and physics? Or in the case of your work, mathematics and biology. And this leads me to the question, which I'll open to the floor. Do you know of any modern day parallels to this story, where one person supplied the tools, one person supplied the politics and the power, and they kind of fell out? Maybe you don't want to air it publicly here. But I think this set of questions is something that I at least want to continue thinking about. Thank you for your time. So yeah, any questions? Samira?
No, I was just going to say that I don't need to say it. It's important. Any questions?
That was great. Many thoughts, but one is that not much has changed, and every one of us knows several examples, so it's not at one level, it seems like a very modern story. And therefore this particular story was elevated by the stature of at least one of the people involved in it. But not by the nature of the interactions of the disputes. And the idea of mathematicians being tools, again that power imbalance is that it may not be mathematicians today, maybe somebody else, but that power imbalance is always there. It may also flip around, and these things go back and forth. But what I wanted to ask you was, so Bhabha, this was not his only contribution, so he did many things. And so for him, this may have been a non-issue. Is that an interpretation of this? This was just an irritant. It has been his only contribution, he may have engaged with it more.
I'm sure that's true. I mean, this is something Anjali had pointed out, that, I mean, if you read through the Madhava Rao papers, Bhabha is everywhere. He's a constant. But if you were to look at the Bhabha papers, which I actually haven't done yet, I'm not even sure that Madhava Rao would appear as more than a single letter or two, right? So, you know, it's a footnote in his life, and I don't think he would have thought of Madhava Rao at all. There's one letter we have from the 1950s from Bhabha to Madhava Rao, and it's a generic letter, no doubt typed by a secretary, thanking him for his participation in Indian Mathematical Congress, and it's just been hastily signed. You know, there's no mention of health problems, there's no mention of when I'm coming to Bangalore. Whatever intimacy, whatever closeness they'd had as friends beyond colleagues seems to have dissipated by at least 1942.
So much for this. When you talk about this collaboration between mathematicians in the early 40s and the physicists, do you point to any other sort of similar? I'm just curious to know what were the other sort of conversations like at that time, and how did they unfold? So, because you're talking about this idea of collaboration, and I was wondering if things spun a different way at that point, where Indian mathematician is not seen as a tool, and it does become collaboration, or maybe there's a retraining of physicists. So I don't know, just sort of hypothesize. There are other examples I love.
Yeah, so I mean, the counterexample to this story, or the set of counterexamples, probably happens at the University of Göttingen in Germany, where, I mean, mathematicians have a much higher stature than physicists. So most of the mathematical machinery that was used by people like Hermann Weyl and whatnot had actually been originated by mathematicians a generation before. So in that case, it's two things. It's this temporal lag. It's the fact that most of the mathematical machinery has already been worked out. And for the more general theories, you have to make reference to this. So, I mean, Hermann Weyl is making reference to the work of a guy called Grassmann, who was writing in the 1860s about like abstract algebra and categories, and at the time nobody understood it, right? The reason it works out in this way between Bhabha is because, at least for that one paper on the scattering of mesons, Bhabha is working out a particular calculation, right? And so he needs to learn these kinds of methods. The most famous example I could think of would be the interaction between Albert Einstein and David Hilbert at Göttingen. So when after special relativity in 1905, Einstein tried to generalize this theory to general relativity, but at the time he didn't know the mathematics of what are called tensors, which you can basically think about as these matrices, but in more dimensions. And so Einstein needed to learn tensor calculus and what is known as Riemannian geometry, that is geometry on surfaces which are not flat but curved. And so he did that in collaboration with other mathematicians active in Germany who were of stature great enough that, I mean, he credits them and speaks quite fondly of them.
Marcel Grossman. He
Hmm?
collaborated with Marcel Grossman.
Yeah, also.
The action that Hilbert action was written by Hilbert 4 days before Einstein.
Yeah.
And so was Madhava Rao aware of the physical context in which those calculations were being worked out?
I think so. I mean, he makes constant reference in his, when he writes the Nieto, he says, what I really like about the paper is that it focuses on the physical implications of this mathematics and doesn't get derailed by, these abstract mathematical considerations. But you get the sense that that's something that people have said to him a few times, and so he's learned to focus on the physics. As far as the scattering of mesons and whatnot, it's fairly clear that he knows the context for what's going on. His paper was on Born's field theory, but on the sort of the poles within Born's field theory, so these divergences, and so he clearly knew the physical picture of what was going on, but focused on these questions of rigor and simplicity, which sometimes led him astray.
Yes. As you mentioned, his relationship with Sarah Bhabha was very different from Madhava Rao.
Right.
What do you think this stems to? Functional privilege? Functional
Class, I think. I mean, sure, they were working more closely together. Bhabha's early work was on cosmic rays. That's the connection in which they collaborated. But they were also similar kinds of people, right? So, you can imagine that a relation of intimacy develops more easily between, what you might uncharitably call princelings than it would, with a guy who did his PhD at Calcutta and not Cambridge, right?
The Riemannian geometry brings to mind a very positive collaboration spaced by time between Perelman and Hamilton. Perelman refuses the Millennium Prize because Hamilton has better equal contribution in the Poincaré conjecture.
Yeah.
So positive collaborations do exist. Just an example.
Yeah, no, all kinds of collaborations. I mean, in the case with Gregory Perelman, he, was a particular kind of character, so, but was there
That was in collaboration between Perelman and not just that. Yeah, he referred to Richie Flow. Positively. He said, I will not accept the prize. Yeah, because Hamilton, according to him, he had already worked out.
But it brings into focus this larger issue of who has done what, right? If you take enough steps back, it's not clear who made each of the bricks, right? This is, it actually becomes an issue of controversy with Sudarshan, who famously doesn't get the Nobel Prize.
What's the sociological reason why credit is so valued in academia? So, when does this notion arise, and does it serve a purpose for at least incentivizing research and collaboration? As to the last question of incentives, it depends on the person.
Some people are motivated by like material reward, some people are after something more abstract. I mean, sociologically speaking, it's the reward structures that exist within academia are totally individual, but the structures that create knowledge are not, right? And so there's an incompatibility in some way. I mean, yeah, you can give the Nobel Prize to a few people, but this history of science is told as the history of gods and giants, right? I mean, this whole era of the 1930s and 40s, people have become so dehumanized, right, that you can't see them as people. It's totally masculine, it's totally based on a particular logic of conquest, really, right? And, go on, sorry.
Yeah, no, so is there's a case to be made that, for example, privatization of property could be used to extract more value from existing resources. So one could argue that that's why a common convention came up to privatize. So here, as you said, it's misaligned. So everything about it seems like it needs fixing. It needed fixing a long time ago. Yet it sort of persists.
Yeah.
So it's mysterious why it still managed. So you're bringing it all the way down to individuals and their egos and a few people who want to benefit from the system. But there must be some larger reason why it survived so long. And it could be just because you don't pay academics anything. I mean, that could be a reason. But there must be some broader theory of why credit has become so central to the enterprise.
I mean, I guess
it's not true in some parts of the arts. It's not true in other areas of human endeavor. Even in other places where it's not possible to attribute individual credit.
I mean, the first thing I'd say is it's true sometimes and it's not true at other times, right? And it varies. There are moments in which nobody's caring about credit, everybody's trying to solve a problem. But after the fact, when what you found standing against the coal face with your pickaxes turns out to be a rare diamond, well, then you start squabbling, right? Then you might get out your knife and knife the guy who helped you get up the cliff. The other thing I would say is you will have to follow the money, right? I mean, when what happens in physics through the course of the 20th century, especially after the rise of nuclear physics and whatnot, is that it becomes clear to states and political actors that you can use this stuff to kill people. You can kill people more efficiently and on a bigger scale than ever possible, right? And so huge amounts of money start flowing in to the most abstruse parts of physics, because the notion that's being sold after the war is that if you let us work on this really abstract stuff, what you will get is power, right? If you stare inward into the atom, you can unlock things. So there's a kind of Pandora's box logic, right, that state actors are working with. And that changes the landscape of what gets funded.
Any more questions?
Sad note to end on, but
I don't have a question, but it's more of a comment.
Great.
So, I'm a mathematician, perhaps to get Harishchandra and his collaboration with Homi J, because the fact that Harishchandra goes on to his PhD in Cambridge, he works with Madhava Rao and Bhabha at IISc, and then they have very different careers. Like the two people who collaborate with Bhabha, Harishchandra and Harishchandra goes on to collaborate with Dirac, goes on to
yeah, so I mean, we're trying to track down the Harishchandra papers actually, and it appears that there was a falling out between Harishchandra and Madhava Rao as well, which kind of supports this theory that, I mean, Madhava Rao gets sidelined in some way. He doesn't have access to these circuits where you can hear a rumor from somebody about what to follow up on, right? I mean, you can work on something that is really important but that nobody cares about, And if nobody cites you, if nobody hears about it, it's going to be hard to get promoted. It's going to be hard to get funding. It's going to be hard to get a permanent job. So I mean, to go back to the question earlier, it has to do with how these questions of individual precarity and all of the things you have to do to get a job and keep a job depend not necessarily on what the most important, what the most abstract, what the most beautiful thing is, but the thing that everybody cares about. That's what's going to give you the job, right? I'm not advocating for that, but you know, the world is already here. It's kind of how it works, unfortunately. Sometimes.
Madhava has applied for a job at Archival and Bhabha is
Yeah, Madhava Rao is totally sidelined. He doesn't get a job at TIFI, he doesn't get a job at IISC, you know, so he becomes a kind of a victim of what it's not clear.
Yeah, thanks Prashant, and thank you everybody for coming today. And also to the Simon Center for accommodating everybody. And I believe there is tea and snacks close by, so we can carry this discussion outside as well. Thank you everybody. Thanks so much, Prashant.
Thanks everyone. Thanks for coming.